Okay, so hello everyone. In this class, we will quickly do a recap of what we studied in the last class, and then after that, we will be actually studying the topic that is planned for today, which is hierarchical clustering. The intention is to not do a 2-hour class because the intention is to complete the syllabus. It might take more. Most likely, it will take lesser. So we will actually cover hierarchical clustering, and as usual we'll solve some questions that are important for your exam, and then we'll end the class. So the class will might take my plan is to cover it in an hour and another 30 minutes for the questions. So let's begin the lecture. In the last class, as you know, we covered partition-based clustering, which is one of the mechanisms to do clustering. Partition-based clustering, we looked at something called k-means clustering. There is a derivative to k-means called k-medoid clustering. And we looked at these two types of clustering, and then the plan was to actually we looked at these two types of clustering, and then we solved some questions. Today we will be actually going into hierarchical clustering. Now, the main thing about hierarchical clustering, so let's begin, is so the main thing about hierarchical clustering is that you actually do not want to know the number of clusters beforehand. So as you know, in the partition-based clustering, whether it be k-means or k-medoid, the value k denotes the number of clusters. And for that, you have to know that beforehand. In hierarchical clustering, you do not need to know the number of clusters beforehand. And it kind of works in a very simple manner. Um, so there are two types of clustering you have in your hierarchical clustering. One is called top-down clustering, one is called bottom-up clustering. So let's begin. So first is you have something called top-down clustering. So again, let's say we have a data set D of n points from x1 to xn. Okay. If you look at top-down clustering, what happens here is that first we consider the entire data set D. Okay. And based on some similarity measure, we divide this data set D into two clusters. Okay. Then we take this cluster A1, we again divide it into two clusters depending on some similarity measure. We call it A3, A4, and so on and so forth. So finally, the leaves of this tree will contain your individual data points, x1 in its own cluster, x2 in its own cluster, so on and so forth, xn in its own cluster. Now, whatever level you are in the tree, that can also tell you the number of clusters you need. For example, if this is level 1 of the tree, if this is level 2 of the tree, level 2 of the tree gives you two clusters, A1, A2. Level 3 of the tree will divide this cluster into more than two, actually, it will divide into four clusters. So, depending on the level of the tree, your number of clusters will be decided. Okay. So, or maybe you can take two from here, one from here, A2, you can take it as it is, that will be your L3. That is also a valid partition. This is about top down. Another way, what you can do is you can do something called as bottom up. So what is bottom up, which is there in your syllabus also? So bottom up clustering, you start from the individual data points as one cluster. So each data point is one cluster. X1 is one cluster, X2 is one cluster, X3 is one cluster, and so on and so forth. Xn is one more cluster. And what you do is you gradually try to merge two clusters, two similar clusters. Let's say if X1 and X2 are the similar cluster based on some similarity measure that we will learn, X12 is a merged cluster. Let's say X3 and maybe X5 is one, then X3, X5 is the next one. Similarly, like this, you go on and go forth. Finally, you get the data set as the final output, the full data set as the final output. This is there in your syllabus, and we'll focus more on bottom-up clustering. Top-down only you need to know what it is. There are types of different top-down clustering which you do not need to study. Only you have to study bottom-up clustering. So basically, the bottom-up approach right? Now, what we do is, given a data set of endpoints, we begin with n clusters. We begin with n clusters, and where each feature vector, we also call these individual xi's as feature vector, where each feature vector forms a cluster. Okay, start with the n feature n clusters, and each feature vector is a cluster. Now you repeat the step 3, the next step, n minus 1 times. Okay, please think through why you need n minus 1 time. I'll give you some hint also. So if you look at the diagram, again, we'll explain this later, but try to think, pause the video and think why n minus 1 before going forward. And what is the step 3 that you want to do n minus 1 times? You find the most similar pair of clusters and merge them. Okay, so most similar pair of clusters and merge them. Now, typically, one of the you might ask me a question that was what is meant by similar pair of clusters, right? So we'll go to that. We'll wait for some time. So typically, why n minus 1 times is you first started with n data points, right? You selected a pair and merged them to one cluster. Okay. Then you may take this one and merge it with this one as the next similar cluster. Okay. So on and so forth. So when there are n points here, you take two of them, merge them to one. So how many remain? N minus 1 remain. Then n minus 2 remain. Then n minus 3 remain, and so on and so forth. Finally, you have your single remaining, which is the entire data set. So there are two things of this tree, that the tree is, first of all, very important point, it's a binary tree, because every time you're merging in pair, so every parent has at most 2 children, so it's binary tree. And the second, the height of the tree is n. Right? The height of the tree is n. Okay. Now the entire concept, this concept is to actually try to find out using bottom-up approach, try to cluster data points And as I said, you do not need to pre-decide, or you need not decide the number of clusters beforehand. Okay. 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 Now, as I said, finding the most similar pair of clusters, which also means to find out the similarity measure. And how do you actually find that? And also, depending on how you consider a representative of a point in a cluster, there are three types of clustering. We'll go into that. If it does not make sense, we'll go through example only. I will not teach you technical jargon. First, I will teach you the concept, then I will tell you the technical jargon. So, the first thing is finding the most similar pair of clusters. Right? And this is nothing but similar to your similar to your partition-based clustering. You use the distance matrix. When do you say that two clusters are similar? When the distance is the minimum. Distance between the points is the minimum. Distance matrix. And I've already taught you the distance matrix in the last class. Hope you remember them. Euclidean distance and Manhattan distance. There are others also, Minkowski distance, Hamming distance. You don't have to study them. You just learn Euclidean and Manhattan. That's enough. So use distance matrix to find out two similar pair of clusters. Now, if you have, let's say, n points in a cluster, let's say x1, x2, x3, right? And I want you to calculate the distance of this cluster from x4, x5, and decide if x4 should merge in x1 in this cluster, or x5 should merge in this cluster, right? So if you try to find the distance, how do you take the distance? Do you take the minimum distance? That is, let's say if x3 is minimum to x4, do you take that? Or do you take the maximum distance? Let's say if x1 is maximum to x4. So which one will you take to actually find the represent? Because if you want to calculate distance from x4, either you'll get a distance d1 from x1, you'll get a distance d2 from x2, you'll get a distance d3 from x3. Similarly for x5, right? Maybe it's x4 or x5, you'll get these three distances. Now, do you consider the minimum distance? Do you consider the maximum distance? Do you consider the average distance? That is what differentiates three types of hierarchical clustering. One is, we'll solve with an example and things will be super clear. If it doesn't make sense, just hold on, okay? Three types. One, single linkage. Two, complete linkage. Three, average linkage. Okay. Now what we'll do is we'll just take an example and then try to learn what happens in single linkage, double linkage, single linkage, complete linkage, and average linkage. So first let's take the data set. Okay. The data set is this. Okay. So for simplicity, the distance metric that I select is Manhattan distance. Okay. Only for simplicity. Okay, now flip your notes, try to see what is Manhattan distance. distance between 2 points x and y is summation I equal to 1 to n or 1 to d, sorry, 1 to capital D xi minus yi. Okay, xi minus yi. Now let's take an example data set D. There are two columns x and y. These are individual points in the Cartesian plane. Okay, they are not supervised labels. Okay, don't be, they are in the territory of unsupervised learning. So 4, 4, 8, 4, 15, 8, 24, 4, and the last one is 24, 12. These are your 5 points in the data set. Okay. Now there is a game called distance matrix. We create it for every iteration. So this is the first iteration. Okay. And let's say I'm talking about single linkage first. Okay. Single linkage. Okay. The first thing that you do is you draw something called a distance matrix. What is a distance matrix? It is an n by n matrix. So n by where is n is the number of samples in your data set. So there are 5 samples. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now it's very simple to know that the principal diagonal of this matrix will contain zeros because the distance of point 1 to 1 is 0. Distance of point 2 to 2 is 0. Distance of point 3 to 3 is 0. Distance of point 4 to 4 is 0. Distance of point 5 to 4 is 0. Okay. Now, with this is done, now what should you fill here? You should fill the distance of point x1 between the points 1 and 2, p1, p2. So this two distance, right? Using the Manhattan distance, right? If you calculate, you get the answer as 4. Similarly, distance between 2 and 1 will also be 4. Distance between 1 and 3, if you calculate, it is 15. Similarly, 3 and 1 is 15. Distance between 1 and 4 is 20. Distance between 4 and 1 is also 20. Distance between 1 and 5 is 28. And distance between 5 and 1 is 28. Okay. Now distance between 2 and 3, if you calculate, it is 11. Right? 4 plus 7, 11. And distance between 2 and 4 is 16. So you'll also fill 11 here, 16 here. Distance between 2 and 5 is 24. And so you'll also fill 24. Distance between 3 and 4 is 9, 13. So you place 13. Distance between 3 and 5 is also 13. We place 13. Okay. Distance between 4 and 5 is 8. So you fill 8. Okay. This is the distance matrix, the distance of every point to every other point. Okay. Now, you have to find the most similar pair of clusters. Okay. Most similar pair of clusters. So who are the, how do you find that? Which has the minimum distance? Always you take, okay. There are two things here. When you're trying to calculate the most similar pair of clusters, you only take the minimum distance. There's no role of single linkage, complete average. All three are the same here. So by looking at it, we see that obviously 0 you won't take. So you will take the point between 1 and 2 as the having the most minimum distance. So what will happen here is if you have the points 1, 2, 3, 4, and 5. So 1, 2, 3, 4, 5. Right? First you are trying to merge 1 and 2. Okay. Why I write like this, I will tell you. There is a name to this diagram. We'll go to that later. But for now, I think it should be okay. Now, thus in the second iteration, you have 1, 2, you have 1, 2. Right? You have 3, 4, 5, you have 3, 4, 5. Okay, now distance between 1, 2 and 1, 2 is 0. Distance between 3 and 3 is 0. Distance between 4 and 4 is 0. Distance between 5 and 5 is 0. Now, if I want you to calculate the distance, now here's where the game of single linkage comes into play. So, the distance of the point 1, 2 to 3 will be what? Okay, now for single linkage, we take the minimum, which is the minimum of distance of 1, 3, comma distance of 2, 3. So what is the distance from 1 to 3? What is the distance from 2 to 3? We take the minimum. So if you look at the previous diagram, distance between 1 and 3 is 15. Distance between 2 and 3 is 11. So which one will you take? You will take 11. Please keep this in mind. This is the only difference between single linkage and the other one. So here, this is because of single linkage. Okay, clear? Okay. Others will, you may calculate, and I will encourage you to calculate on your own. So this will also be 11. Distance from 1, 2 to 4. Find the distance between 1 and 4, which is 20. Find the distance between 2 and 4, which is 16. Who is the minimum? The minimum is 16. 1, 2, and 5. So what is the distance 1 to 5? 28, 24, 2 to 5. So we take 24. Okay. And now 3 to 4, we can only copy it already from the previous one, 13 and 13. So this is also 13 and 13. 4 and 5 distance is 8. And so distance is 8. Okay. Now again, you find the most similar pair of clusters. And who are the most similar pair of clusters, guys? This 4 and 5 will be my next piece in the will be the next most similar pair of clusters. Now, how do you draw it is, so this is 1, this is 2, this is 3, this is 4, this is 5. So you already had joined 1 and 2, so I'll keep this as joined. Now you are planning to join 4 and 5, so you will actually go here and join them. Okay, why do we do that? I will go to that later on, but just for now. So this line, right, this line that I have drawn is in the same level as this circle, parent. Okay, why I do this, I'll explain you later. Don't worry. Okay, just for now, follow along. Whatever I say, just believe me. Later on, we will explain everything clearly. Okay, now this is D. Now we go to the next iteration, which is C. Now we had 1, 2, right? 3 is still standalone, and we have 4, 5. We have here our 1, 2, we have 3, we have 4, 5. Distance between 1, 2, 1, 2, 0. Distance between 4, 5, 4, 5 is 0. Distance between 3, 3 is 0. Now, distance of 1, 2 to 3, we can copy it from the earlier case. It is 11. Distance between is also 11. Okay. Now it's an interesting thing again. The distance between the points cluster formed by 1, 2, comma cluster formed by 4, 5. This will be nothing but the minimum distance of, can you take a guess, of the cluster 1, 2 to 4, comma the distance of 1, 2, 5. Understood? And we already calculated these distances in the previous iteration. So if you do that again, you will get this as 16. This will be 16. Okay. Now distance between 3 and 4, 5 will be, take the distance between 3 and 4, take the distance between 3 and 5, and then you take the minimum, so which is 13. Okay. Now, so who is the next candidate? As you can see, 1, 2 will be paired with 3 because it has the minimum distance. Okay. Now, I'll just move this a bit down. I'll move this down. Okay. Now, and then we'll draw the cluster, the diagram. So we have our 1, 2 still there, 3 is there, 4 is there, 5 is there. So 1, 2, I'll join them and connect with a line. Again, 4, 5, I will join them, connect them with a line. Okay. Now I'll take 3. Okay. And roughly it should be on the same level as this, right? So I'll take them and join them like this. Okay. Now, as you see, we have got this. Now I can go ahead and do the iteration, but as you see, the next one will definitely be you join this with this, right? Because there is no more cluster that remain. Okay, there's no more cluster that remain. Now we kind of got this diagram, and what do we get, right? Partition based testing, we actually got the data points that are there, but what do we get with this? See, first of all, this diagram is called the dendrogram. Okay, it's called the dendrogram. You know what's the coolest part of the dendrogram? See, let's say you want only one cluster. One cluster as in you just need the entire data set. You place a parallel line and cut through the first one. Now, whichever points are connected, find the connected components of this graph or this tree. Tree is also a graph, right? Graph with some special property. Find the connected component. As you see, there is only one connected component, right? Every node is connected to every other node. So this, if you cut it here, you get one cluster. Let's say I want 2 clusters. I'm not happy with one cluster, I need 2 clusters. So I'll cut through here. I will cut through here. So I will get 2 clusters. How do I get 2 clusters? See, this is my one cluster containing the points 1, 2, and 3. Okay. This is my one cluster. And this is my one cluster containing the points 4 and 5. Okay. One cluster is this, another cluster is this. So these are 2 clusters. Okay. Now, let's say you are not happy with 2, also you need 3 clusters. I cut through here. Okay. I got 3 clusters. How? See, this is one cluster containing the points 1, 2. This is one cluster containing the point 3. And this is one cluster containing the point 4, 5. Similarly, if you need 4 clusters, you cut the next one. You need 5 clusters, you cut the next one. So this is the most beautiful part about the dendrogram. And this is single linkage form of clustering, where if you want to calculate the distance of a cluster to a point or to a cluster, you take the minimum distance. Now, if you take the minimum distance, you get the least separation between the clusters because you are considering the point which is very close to a cluster, right? So it has minimum separation. But if you need to separate things more, then we go with something called complete linkage algorithm. Now, what is a complete linkage algorithm? Now we'll do that. Okay. Any questions before I go ahead? I'll give you some time to think. Take some time out. I'll just open the slide for you. Take some time out. Give you. I think I'm rushing a bit more. I should slow down a bit. So I'll take this time. I'll give you a 5 minute break. Okay. You may seek this video if you are watching it online later on to 5 minutes from now, and you will find me talking about this cluster, the other type of clustering. Otherwise, I'll just give you some room to think about, write the diagram, note down things, learn them now, and then we'll meet after 5 minutes. Okay. Okay, so no questions. You understood. Good. So let's go ahead and look at complete linkage. Good that you understood. So let's go and look at complete linkage. We'll do the same data set, but with complete linkage now. So the first step remains unchanged, which is the distance between individual points will not be changed, right? So we're looking at complete linkage. Okay. And in complete linkage, your first step remains unchanged. So you again draw the matrix 1, 2, 3, 4, 5, 2, 3, 4, 5. Difference of individual points with itself is 0. 0, 0, 0, 0, 0. 4, 15, 20, 28. 4, 15, 20, 28. 11, 16, 24. 11, 16, 24. 13, 13, 13, 13, 8, 8. Right? And then the first step also remains unchanged. You merge 4 and 4. Okay. Now, then the second step, please pay attention. So 1, 2, 3, 4, 5. 1, 2, sorry. Sorry. I think it should be 1, 2. Yeah, okay. Distance 0, 0, 0, 0. Okay. Now the distance of 1, 2 to 3 will be now not the min, but the max of distances between 1 and 3 and 2 and 3. And if you see, it is 15. That's where difference comes in. So this will be 20, 28, 20, 28, and the others remain unchanged. Distance between 4 and 3 is 6, 13. Distance between 3 and 4 is 13. Distance between 3 and 5 is also 13. Also 13. 4 and 5 is 8 and 8. Now you select still the most similar pair will be the minimum. So you select this and this. Okay. I'm not doing the next steps. I think you got the idea. And for average linkage, instead of not taking the min, not taking the max, you take the average. You take the average. Okay. So this was about single linkage, complete linkage, and average linkage. Now I will suggest you guys to try to do this. Try to solve the same question. You may try to use Euclidean distance instead of Manhattan distance. I just wanted to teach you the concept. That's why I gave Manhattan distance. I could have easily done with Euclidean distance as well, but the idea is not that. Idea is to go with Manhattan distance as well. Okay. Okay. Any questions? No questions? Okay. Now, in the last year GATE exam, there was one question asked from this topic, hierarchical clustering. I wanted to discuss it here. So I will give you some time to solve it on your own. Take some like 5 minutes to solve. Try it out. I think it's related to what I taught you today. So it should not be very difficult, but still, let's see if you can answer. So 1 second, I'll just see where the question is. I think I pressed the yeah, okay, fine. So I think it should be 1 second. 15, 16, 17, 18, 19, right? Yeah, this I think will be the question. The question was given in GATE 2024 last year. Try this out. I'll give you 5 minutes to solve. Okay, what is the answer? The answer is option A. Good. Yeah. So what you do here is A or B. Let's see. Let's see. I don't remember. Let's see. Okay. They are saying consider the table below. Uh, Single linkage is performed on the data set. So which one of the following is the correct representation of the clusters produced? Now, as you see, first step, you will have x1, x2, also x4, x5 merged. Okay, because all these two pairs have the same distance, which is a minimum distance as well. So you have your x1, you have your x2, then you have your x3, x4, x5. Okay? You merge these two, you merge these two. Okay. Now, how does my distance matrix looks like? It's 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. Now, distance of 1, 2 to 1, 2 is 0. Distance of 3 to 3 is 0. Distance of 4, 5, 4, 5 is 0. Distance of 1, 2 to 3, single linkage, you take the minimum distance from 1 to 3, 2 to 3, which is 3, right? Which is 1 to 3, distance is 4, 2 to 3, distance is 3. You take the minimum, which is 3. 1, 2, and 4, 5, distance of 1, minimum of 1 to 4, 1 to 5. 1 to 4, distance minimum is 3. 1 to 5, distance minimum is 3. So the minimum distance is 3. Okay. Now distance of 3 to 4, 5, minimum of distance from 3 to 4, 3 to 5. So which is 2, 2. So which is the next candidate? Next candidate is 2. So you merge this 3 with this 2. Okay. And then certainly you will merge these two. Right? So which one is the correct answer? A is the right answer. Okay, good. Now we go to the gate questions that are there, some important questions for your exam, which I think you should solve, even it's a gate DA paper. The format of these would be there are about 6 questions, I guess, 6 or 7. Let me just think 6 questions. Oh, okay. There are 9 questions. Okay. First question we already did. Total 10 questions were there. 9 questions, 3 minutes per question I will give you, and the rest 3 minutes we will discuss the 2 minutes we'll discuss the answer. So 5 minutes per question we will do. 9 minutes, that will be about 45 minutes of your work. Okay. Starting with this question, please try this out. Your 3 minutes start now. Yeah, this is a simple question, right? So what is a sample space S? The sample space S consists of 36 outcomes. You are rolling a dice twice. What is the probability of getting a sum of 7? So what are the outcomes favorable to the event? One is 2, 5, 3, 4, 4, 3, 5, 2, and also actually 1, 6, 6, 1. Any other that I'm missing? No, right? Yeah. So six outcomes are there. So the probability of the occurrence of A is 6 by 36, which is 1 by 6. Okay. Now, when I was studying for the CAT, I tried it for some time. Someone told me there is a pattern followed here. The number of favorable outcomes to get a sum of X. So 7, 8, 9, 10, right, 11, and 12. You can't get less than 2, right? Rolling a dice twice, so minimum sum we will get as 2, maximum we will get as 12. And to get a sum of 2, minimum is 1 outcome. For 3, it is 1, 2, and 2, 1. So there are 2 outcomes. For 4, it is 1, 3, 3, 1, and 2, 2. So 3 outcomes. For 5, it is 1, 4, 4, 1, 2, 3, 3, 2. So there are 4 outcomes. For 6, it is 1, 5, 5, 1, 2, 4, 4, 2, 3, 3. So there are 5 outcomes. For 7, it is 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3. Right? So there are 6 outcomes. Now when it comes to 8, it is 2, 6, 6, 2, 3, 5, 5, 3, 4, 4. So it is 5 outcomes. For 9, it is 3, 6, 6, 3, 4, 5, 5, 4. There are 4 outcomes. For 10, it is 4, 6, 6, 4, 5, 5. There are 3 outcomes. For 11, it is 5, 6, 6, 5, 2 outcomes. And for 12, it's only 1 outcome. If you see, it's a pattern, right? It increases, it starts low, it first increases till 6, 7, and then it decreases. It's a pattern that is followed. Okay. So that's why you can also, many people learn this pattern only to actually answer the question. So it's much more fast. Okay. Next question is this. Your time starts now. Yeah, what is the answer? Which evaluation metric is commonly used for classification tasks when class imbalance is present? So everyone knows what is class imbalance. So first of all, class imbalance means, so if you have a binary classification problem where your y can have either the value 0 or 1, true or false, cancer or benign, or right, some binary output. So let's say, for example, you are trying to measure the accuracy. Okay, it's a class imbalance data set. Okay, now let's say you have 100 data points. Okay, you have 100 data points. Okay, now the class is heavily imbalanced, which means 98 of the points are actually the class is 1 for it. Okay, the last 2 points, the classes are 0. Okay, now my model is y bar equal to 1. Okay, very simple model. I am not doing any machine learning. I'm just saying whatever sample I get, I will get the y bar as 1. Okay, what? So mean squared error is something used in regression. So you can omit this. R squared is also something used in regression. You can omit this. What will be the accuracy of the model? Training accuracy? Can anyone tell me? So how many? So all these are predicted as 1. All these samples are predicted as 1. Even this as well. So out of 98 samples are correct, out of 100 samples, your accuracy is 98%. So this should be an amazing model, right? Because accuracy is the best, 98%, right? But as you see, this is not even machine learning in the first place. So accuracy is not the right answer. F1 score actually is very helpful to measure the class imbalance as well. Okay, this is a very important technique. Hope you understand the concept. Okay, let's go to the next one. Your time starts now. Okay. So what is the purpose of validation set in machine learning? It's a very simple question. It's not used for training the model. It's kind of used for training the model, but you also can do it with train set and test set. So it's not the right answer. To test the model generalization, maybe. To provide additional training data, certainly not. You don't use it to build the final model. You kind of use it to tune your hyperparameters. So if you have seen a machine learning model, for example, if you have seen, let's say, random forest, how many trees you want, what should be the depth of the tree you want, right? All these are hyperparameters, which are parameters that you use to build the model. They are not learned, they are decided beforehand. So which hyperparameter works best? That's called fine tuning the hyperparameters. You may use a validation set to fine tune your hyperparameters. This is the next question. Your time starts now. Yeah, so it's a direct question, right? You people, you should know this. It's directly from the Poisson distribution. If the number of trials given is t and s is the probability of success, the mean value, the mean is t multiplied by s, ts. Okay, so option B will be the right answer. Okay, I'm facing some issue with my iPad. I'm seeing the slides. I'm just marking it through my uh, PC. So the this is directly from the Poisson distribution. Okay, good. If you could answer it, it's the same question, is it? Second. That's the same question. Sorry. Okay, one question less you have. Which of the following? This one, let's do it quickly. I don't want to waste time. Which one of the following is not a type of supervised learning algorithm? So we are in, as you saw in the last lecture, we talked about k-means clustering, which is one of the classical examples of unsupervised learning algorithm. So option C will be the correct answer. This is the next one. In the context of databases, what does ACID stand for? I'll give you a minute. Yeah, so it's an easy question. So in the context of database, ACID stands for atomicity, consistency, isolation, and durability. Three more questions. Okay, if you guys can see the slide, please try to answer this. What is the rank of this matrix? Yeah, so what is the rank of this matrix? It's very easy. There are multiple ways to solve this question. If I were you, I could directly say the rank is 1 because there is only one linearly independent row. But let's say you don't know that. What you should do here is you should write the matrix and reduce this matrix into something called row echelon form. Okay. So what is row echelon form is you consider one of the element as the pivot. Let's say I consider this element as the pivot. Okay. Now I would maybe want to do some row operations to make something zero, something's not a zero. So I would want to convert it into a, I will want to convert this into a, sorry, convert it into a lower triangular, upper triangular matrix. So I would want to make this thing as zero, also this thing as zero, right? So how can I do that? I will, oh, sorry, the answer is not actually 1. Okay, let's look into it. Okay, this matrix has changed a bit. So yeah, so let's say I want to make this as 0. So I'll maybe do row 2 is row 2 minus 4 row 1, right? So I get 1, 2, 3. First row is unchanged. Second row becomes this, becomes 0. 5 minus 4 into 2, 8, which is minus 3. 6 minus 4 into 3, minus 12, so minus 6. And then we kind of do R3 is R3 minus 7 R1. So it becomes 0. 8 minus 2, the 2 into 7, 14 with minus 6. 9 minus 3 into 7 is minus 12. Okay, now you see, right, what's going to happen. So now this is a 0, this is a 0. So you want to make sure that you make this as 0. So you will consider this as your next pivot. And if you make this as your next pivot, it's a very simple operation. I can do R2 gives, sorry, R3 gives R3 minus 2 R2. Okay, and I get 1, 2, 3. Second row remains unchanged. Third row will fully become 0. And if you get, and now once you have done this, you cannot proceed any further. You have taken one pivot from the first row, one pivot from the third row, second row. You cannot take any pivot from the third row because everything is 0. So number of non-zero rows is 2, rank is 2. Okay, good. Next question is this. If a neural network has 3 input neurons, 2 hidden layers with one. Okay, please try this out. We'll give you some time. Okay, so you draw the architecture, it will be easy, right? So you have 3 input neurons, 2 hidden layers with 4 neurons each. So this is one hidden layer, this is another hidden layer, and you have an output layer with 2 neurons. Okay, now how many weights does it have in total? Assuming fully connected layer. Weights actually, yeah. So first this, it will be connected with all 4. This will be connected with all 4. This will be connected with all 4, right? So this one we have 12. Okay, hold on. There is one more thing here. Hold on. Okay. Now this is connected to all 4, all 4, all 4, all 4, and all 4. This is 16. This is connected to 4, 4, 8. Right? So how many weights are there in total? There are 36 weights in total. Is that enough? This is the answer. There is no option, right? So although Gate would have added this as an option and you would have marked and comment, the answer is wrong. Because you also have to consider the biases. So what is a bias? Here is one bias, 1, 2, 3, 4. So this is 4 biases. Here also you will have 4 biases. Here you will have 2 biases. So you add 10 to it. For the bias, you will get 46. 46 is the right answer. This is for your bias terms. Okay. 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 Last question before we end the class is this very simple question: normal distribution. You just need to know a property. What percentage of data falls within one standard deviation of the mean? Okay, so do you know the rule? So rule, if you know the rule, you will be able to answer. The empirical rule says it's also called the 68, 95, 99.7% rule. Yeah, what does it mean is 68 percentage of data fall within 1%, one standard deviation fall within one standard deviation of the mean. So here is the answer. Okay, but still let's write the rule so that you have it in your notes. 95% of data fall within two standard deviation of the mean. 99.7% data fall within three standard deviation of the mean. This is called the empirical. Okay, so the answer is 68%. Okay, uh, any questions before I end the class? Okay, no questions. Okay, so I'll just send you the slides on the chat so you can download them. Meanwhile, I'll wait if you have any questions. If you have, in the next class, we will try to look at PCA, dimensionality reduction, another important topic in your exam, in unsupervised learning. We'll look at dimensionality reduction, and in one more class, I will look into LDA. And I'm not yet planned to look into LDA itself because it takes more than one class, and we have two more classes left. So I'll see. Let's see. Most probably I will take, but if not, then we'll solve some questions in the last class. Or I will actually do the derivation of LDA for you. That will be helpful for your exam. Okay. So also please make sure you are watching the lecture videos that are already published. They are very good lectures, especially at supervised learning. It's very easy. You can see in YouTube also on your also here on the IGC channel. Whichever looks okay with you, please try to see them. You will be able to understand. Okay. Yeah. Okay. Make sure you download the slides. And thank you for joining. We'll meet in the next class. See you. Goodbye. Tata. Bye bye.